So let's review about what we have discussed, or what uh, the activity or what's going on in the last laboratory. So we create a model about nonlinear patterns with activation functions with ReLU. So the problem with the linear models in the previous lab, a linear model worked well when the data involved only bike deliveries. However, once car deliveries were added, the relationship between distance and time become curved, not a linear. So, a linear model can only learn straight line relationships. So, no matter how many linear neurons are added, the output will still be straight line. How many straight line? So, this limitation causes poor performance on the combined bike plus car datasets. So, why nonlinear activation function matters? To solve this problem, the model needs the ability to learn curves, not just straight lines. Okay, this is achieved by using nonlinear activation functions. The lab introduced rectified linear unit, or what we call ReLU activation function, which allows the network to introduce bends in the prediction line, approximate complex real-world patterns, linear-wise, learn piecewise linear relationship that together form a curve. Preparing data normalization. Before training the nonlinear model, the data was normalized using standardization. Discover normalization. Steps performed. Compute the mean and standard deviation of distances and delivery times. Transform the data using value minus mean divided by standard deviation. So compute the mean and standard deviation of this instance and delivery times. So what we does is we prepare the data, or we call normalization. So before the training, the nonlinear model, the data was normalized using a standardization, using a z-score normalization. We compute the mean and standard deviation of distances and delivery times. Transform the data using value minus mean standard deviation. Why this is important? It prevents large values from dominating training. Keeps gradient stable. Make training faster and more reliable. Even after normalization, the shape of the data remains the same. Only the scale changes. Yes, so we do normalization that prevents large values from dominating in training, keeps gradients stable, makes training faster and more reliable. Even after normalization, the shape of the data remains the same. Only the scale changes. Building nonlinear neural network. The model architecture used was input layer, one feature or the distance, hidden layer, 3 neurons, activation. We use rectified linear unit, or ReLU. So, and the output layer is 1 value delivery time. So the structure is the linear is 1 3 ReLU, and linear 3 1. This hidden layer with ReLU is enough to learn the curve pattern in data. Training model. Loss function. Mean squared error. Optimizer is stochastic gradient descent. Learning rate 0.01. Epochs, which is 3000. During training, the model repeatedly predicted delivery times. The error was calculated using the mean squared error. Backpropagation adjusted weights and biases. A live plot showed how the prediction curve improved over time. Final loss was very small, indicating a good fit to the data. Evaluating the final fit. After training, the final prediction curve closely followed the actual data points. This confirmed that the nonlinear model successfully learned the curve relationship that the linear model could not, making predictions with normalized data. Because the model was trained on normalized values, prediction requires extra steps. Normalize the new input distance using the same mean and standard deviation. Pass it through the model. Then normalize the output to get the predicted time in minutes. This step is critical. The model does not understand the real-world unit unless they convert it correctly. Example, result. If we normalize the data, we use it for our model to have a that makes training faster and more reliable, prevents large values from dominating training, keeps gradients stable. So after we normalize the data, we need to denormalize it, the output to get the predict time in minutes. Okay, like for example, 5.1 mile delivery was predicted to take about 38.7 minutes. Since it is under 45 minutes in over 3 miles, the correct decision was to use a car. Key takeaways. Linear models are limited to straight lines. ReLU enables neural networks to learn nonlinear patterns. Normalization improves training stability and performance. Nonlinear neural networks can model real-world data more effectively. Proper normalization and denormalization are essential during prediction.